Okay, so our next speaker is James Wootton from the University of Basel, who's going to tell us about proof of principle experiments for planar.
Yeah, so I'm gonna talk about proof of principle experiments. I don't know if I'm gonna tell you about them. I don't know if I'm the person who can give you any
You're not going to
insights.
do one for us right here?
Not today. Although I did work out how to make non-abelian anyons with dice once. I should have brought my dice along. Anyway, so so I put a paper on the archive today on this. So that's mainly intended to be there so you can look at it. It's not the set in stone, so please ask me about it, talk to me about it, and get me to change things. This is it's done at the University of Basel, funded by QCIP, blah blah blah. So this is all based on my idea now that I, at least, I say we as if I'm the prophet of talking to experimentalists who's here to convert you. But I feel I need to start working with experimentalists. It's very tempting to ask questions where we take the code distance to infinity, use nice tractable noise models, and don't worry about where the wires will go. As David was saying yesterday, it's quite hard for the experimentalist to imagine how to go from 1D to 2D for reasons of where the wires will go. So when you're considering a 3D code, then really how do you get to the ones in the middle? How do you do those stabilizer measurements? So for that reason, I don't think about those. But no, I'm happy for other people to think about them because we should be considering all of the possibilities and not get stuck with our path dependence, of course. Doing these sorts of studies, I don't think they're going to get us a Nobel Prize anytime soon. But the experimentalists who will be getting Nobel Prizes are making very great strides. But they're still far behind infinite code distances. Or even sometimes I make a paper and it's got like a 20 by 20 code. Is the highest one I've done to calculate my threshold. And I think, oh man, that's so small. But in terms of actual physical qubits, that's like 1,000 or so. Yeah, but then you've got your ancillas. You've got your ancillas as well. So yeah, so maybe we should actually start helping the experimentalists in what they're doing, and look at those sorts of problems in error correction. So perhaps you are already doing this. As I said, I'm not the prophet for it, but I'm not really doing this, so it's time for me at least to change and do something that's useful to those people who work on the floors below me with lasers and things. So what I'm doing is I'm considering the simplest example of a surface code that can actually correct quantum errors. And I think it's nothing too new. We've seen it before in a few figures. So I think this is what's going to be done. So if you think it's too complicated or too simple, let me know. But I think this is probably what's going to happen, especially in IBM. And I'm going to use this to find out what sort of noise levels will be needed for the initial experiments where we're not trying to actually build a quantum computer, we're just trying to make quantum error correction work. In this talk, I'm just applying Pauli noise because my conversion is not complete yet. Let's take it one step at a time. But in the future, we'll get better and better, do coherent stuff, and actually do things that mean things to experimentalists. This means getting more specialized, because if you want to talk about actual realistic noise, then you can't do something that applies equally to trapped ion, superconducting qubits, and spin qubits. You have to decide, I'm going to do it with spin qubits, with floating gates, with gallium arsenide, whatever, and look at noise models that apply to that. So that's what I'm going to be doing. Because I'm in Basel, there's a lot of people who know things about spin qubits, so I'm looking at spin qubits. I'm also very much, I've been immersed in the propaganda of spin qubits for many years, so I definitely think they're the best way to go. Even though our experimentalists aren't building the rocket yet, they're still getting everything ready in the hangar, so it'll be out soon. It means we don't have to shout so far when we're shouting up to them as well. Okay, so I'm trying to set this in a more general framework of how I think proof of principle experiments will go, and I consider there to be 3 phases, which are basically, phase 1 is what people are doing now, phase 2 are what people will be doing soon, and phase 3 is what people will be doing after that. So phase 1 involves things like, it's proving that the kind of things we need for quantum error correction can be done, so that we can prepare the required states, we can do the Syndra measurements, we can correct at least some of the errors. And then phase 2 will bring this all together and actually show that we can make a logical qubit which we can prepare in some state, do some stuff for a while, and then measure, read out, and the probability that it is read out in the same state that we prepared it is higher than if we had just used a single physical qubit. So the overall fidelity is better when we use a code than when we use the single physical qubits that make up the code, which currently it's not. And then phase 3, so that will just be sort of a short time scale, as much time as we need to actually do whatever it is we need to do to make this work. And then phase 3 will keep on doing the Syndra measurements. We'll repeat the Syndra measurements and try and keep it going for a longer time scale. So David touched on some of this yesterday, but I'll just talk about the kind of experiments you get currently in phase 1. We have John Martinez's group with superconducting qubits, and they have had an experiment with 9 superconducting qubits, 5 of which are data qubits on the code, 4 of which are measurement qubits, and then they do 2 qubit entangling measurements, so ZZ measurements, mediated by this ancilla. So this is exactly the same way. This is exactly the way that we imagine Syndra measurements to be done. That we've got some data qubits, we get an ancilla between them, and we do some entangling gates and measure out the ZZ observable without actually going in and measuring the 2 Zs separately. So they've shown that, and they've done it on this 1D structure. So it's actually a classical repetition code, but done in a quantum way. So a classical repetition code is just the same as repeating yourself when it's a bad line on the telephone, but they've done it quantum. And so they only correct classical errors, bit flip errors, but they've shown that as they increase the code size, the error rate goes down, which is exactly what you want. We've also, with superconducting qubits, we have the group of Jerry Chow at IBM, and they have similarly done some Syndra measurements. I keep pressing the go forward button when I mean the laser button. So they've similarly got the Syndra measurements. They take 2 data qubits and 2 ancilla qubits, and they use them to do an XX and a ZZ measurement. So this can detect both bit and phase errors, but because it's only on 2 data qubits, it doesn't actually give us a code that can store anything. In fact, it's equivalent to doing a Bell measurement, and of course people have done Bell measurements before many times, but what makes this different is that it's claimed that it's done in a way that is scalable to increasing this to the full toric code, surface code Syndra measurements. So it detects errors, but it doesn't have a logical qubit. So again, it's doing what we need, but not everything we need. And then a few years ago, Rainer Blatt's group in Innsbruck did an experiment with 7 trapped ions. So what they did here was they prepared the state, and they did some tomography on that to show that this state doesn't show you that there are errors, but if you artificially introduce errors and then do some tomography, then you see that the errors are there. So it's showing that the state really does have the capability to show you that errors exist. So in all of these cases, I think they're summed up by this picture, which is that what they're going to do tomorrow is make a color code so big that it can cover an alien world. But, today, just for today, they're going to cut out this little bit, and they're going to do that. And in each case, this little bit that they cut out actually corresponds to something simpler than they started with. So as David said yesterday, this is a steam code. We've got the same sort of picture here, it's a big surface code, but they're just going to do this little bell measurement there. And in this case here, we've got a big surface code, but we're just going to do that line. But none of them show it so dramatically as this one. I also have an idea for a phase 1 experiment you can ask me about if you want. Braiding twists in a surface code with only 5 qubits. So that's similarly, big picture, but we're just going to do those ones. And we claim that it's braiding twists, but yeah, that's not what this talk is about. So what I think is going to happen when we move on to phase 2 and phase 3 is we need to get a system which has as few physical qubits as possible and as few gates as possible, and nearest neighbor interactions typically as well, and capable of both detecting and correcting bit and phase flip errors, which means that it's got to have a distance of 3. So a good solution for this, and so good that we've already seen it a few times, is this d equals 3 planar code. So unlike the normal planar code that you might see, it doesn't have 3 qubit stabilizers on the edges, which correspond to this rough and smooth boundary, but instead it's rotated and cut out again, and then has these 2 qubit stabilizers on the edges. So there's 2 ways, well, there's many ways there's many unitary equivalent ways to do this, but 2 ways that we can think about is we always bicolor the plaquettes, I'm sure everyone knows that. And one way we can do it is to have these ones with X stabilizers and these ones with Z stabilizers, but also we could have all of them a combination of X and Z. So I'll talk a bit more why you might choose one over the other in a little while. So the planar code, I'm sure none of you have heard of the planar code before, so I'll take you through it. It's got this, at least this example's got a distance of 3. It stores 1 logical qubit. It's defined on 9 physical qubits. So here I've shown the physical qubits with black dots. And we also have 8 stabilizers, so the 4 bulk stabilizers, which are 4 qubit, and the 4 edge stabilizers, which are 2 qubit. And if we use an ancilla, a unique ancilla to mediate the measurement of each stabilizer, that means we need 8 ancillas, which are these white dots here. So that means we need 17 physical qubits overall. Now, if we use this ancilla can be used for this stabilizer because it's close to these ones, but it's also close to these too. So you could say that instead of using 2 ancilla here, 1 to measure these 4 and 1 to measure these 2, you could reuse this one. So this one could be used to make this Syndra measurement and then that Syndra measurement. That extends in time your process, but it means that you use less physical qubits. So depending on what's important to you, you could go for that instead. That means you can use 13 physical qubits. And this has been studied in quite some detail and compared with other possibilities in this paper by Tomita and Svor from a few years ago. So the 2 subsets of the stabilizers, as I'm sure you all know, detect different types of error. In this case, if we have a phase flip error, it's picked up by the X stabilizers. If we have a bit flip error, it's picked up by the Z stabilizers. But here it's a bit more complicated. If we have a phase flip error here, it's picked up by the blue ones, and a bit flip error is picked up by the white ones. But if we have a phase flip error here, it's picked up by the white ones, and the bit flips are picked up by the blue ones. So we can use this because in this case, if you have high bias in your noise, if your bit flip error, for example, is much slower, so if they occur at a much slower rate than your phase flip errors, then what you'll have is that this white part is really struggling the whole time to keep up, whereas this bit flip one hardly ever does anything. It's just sitting there having a cup of tea. Every so often it sees a stabilizer and says, yeah, I know what that means. But in this case, they're mixed together, so everyone has to pull their weight. So if you have highly biased noise, then this is likely the one to go for, and we're going to consider biased noise here. So this is the choice of stabilizers that we're going to have. So how do you measure the stabilizers? Well, as typical, you do some entangling gates and use an ancilla. So in this case, you could have an ancilla here, prepared in the 0 state, and then do controlled knots sequentially between the ancilla and all these code qubits. And what those controlled knots do is look at whether the code qubit is 0 or 1 and tell the ancilla, but the ancilla can only hold one bit of information, so it just holds the parity overall. Now, if you were to do the same thing here, what you could do is initialize this in the plus state and use your controlled knots backwards, because a controlled knot backwards is something that looks at the plus-minus states and does a z, depending on whether it's plus or minus. So that's what some people do, but instead we're going to consider always keeping our ancilla in the state 0. And so what we'll be doing is what I call a phase-controlled knot, which is the same as a controlled knot, but with conjugated by Hadamides on the target. So it looks at whether this is plus or minus and does a flip here accordingly.